So our next speaker today is Cohen from the University of Hamburg, and he will speak about bordered Floer theory, Hochschild homology, and links in S1 times S2.
Thank you very much. So my talk today is about an extension of a celebrated result of Peter Oschwart and Sultan Sabo, which establishes a relationship between Chowanov homology, which is a powerful invariant of links in S3, and Heegaard-Floer homology, which is a three-manifold invariant. I've put up a list of several references for the talk if you want to see a mountain of background details that I'm going to gloss over. I intend to commit a multitude of sins during this talk and not define anything and just let you use some mild intuition coming from related objects to the things that I'll be talking about. But I'm not going to list all of these. There are a couple of conventions up on the board. For me, F will always be the field with two elements, and K will be a semi-simple commutative ring of characteristic 2. In other words, it's some direct sum of copies of F spanned by a set of mutually orthogonal idempotents. Okay, so this sort of classical-ish theorem of Oschwart and Sabo states that if L is a link in S3, then there exists a spectral sequence whose E2 page is the reduced Chowanov homology of the mirror of the link with F2 coefficients, and whose E infinity page is the Heegaard-Floer homology of the branch double cover of L. So I'm going to tell you about a version of this for links in S1 cross S2. So in order to do this, I need to talk to you a little bit about bordered Floer homology. So bordered Floer homology is an invariant of three manifolds with parametrized boundary. And I'm just going to tell you about the simplest versions of this. So to a surface, f of z, where z is some combinatorial data that describes this surface together with a parametrization, it associates some differential algebra, which I'll call A of z. For the curious, the data that you need is a circle, an oriented circle, together with a distinguished base point, and a multiple of 4 many distinguished points away from the base point, together with a matching, which determines some handle structure for your surface. And to a three-manifold with boundary parametrized by this surface, so y together with a diffeomorphism from f of z to the boundary of y, it's going to associate what you can think of as a left differential module which we'll call CFD hat of y. Strictly speaking, you need several auxiliary choices here. You need some choice of what's called a bordered Heegaard diagram, which is a combinatorial presentation of the three-manifold with this parameterized boundary. But up to homotopy equivalence, this object is independent of the auxiliary choices. And if you have a three-manifold with 2 boundary components, it'll give you something called CFDA hat of y, which is really one of these things that Ian talked about on Monday, that's some combination of an A infinity module and a differential module. But if you want, you should just think of this as a differential bimodule, and you'll be fine. Okay, so one of the theorems that I use in my construction that I will use is due to Lipschitz, Oschwart, and Thurston, who I will consistently abbreviate as LOT, states that if y1 and y2 have boundary parameterized by the same surface, f of z, then the morphism complex A of, I should have told you that this is over A of minus z. So this left differential module is over the algebra A of minus z. It's not really that important that you've reversed the orientation here, but there are sort of two different kinds of modules that show up. And in this version of the story, I'm going to work over A of minus z. So if y1 and y2 have the same surface parameterizing their boundary, then the complex more from CFD hat of y1 to CFD hat of y2 is the complex of left module homomorphisms with the usual commutator differential, which sends a homomorphism to del 2 composed with f plus f composed with del 1. Note I'm working over f2, so there are no signs present, is homotopy equivalent to the ordinary Heegard-Floer complex of minus y1 glued to y2 along the common boundary via the parameterizations. Okay, there is also a tensor product version of this pairing theorem, which I'm not going to talk about at all. And as an extension of this, last year I proved the following theorem, which says that if for I equal to 1, 2, and 3, I have 3 manifolds yi whose boundaries are all parameterized by the same surface. If I define W to be the so-called pair of pants cobordism given by, well, a triangle cross F where F is, this is going to be F is F of Z. So triangle cross F union along E1 cross F, E1 cross Y1, union along E2 cross F, E2 cross Y2, union along E3 cross F, E3 cross Y3, where, again, the triangle is an actual triangle, with edges E1, E2, E3 in clockwise cyclic order, then there is a homotopy commutative square of the following type. Let's see, do I have enough room? Maybe. With your allowance, I'm going to abbreviate this big morphism space as more a y1 to y2. Otherwise, I absolutely won't have room. I have a homotopy commutative square of the following type. I've got more a y1 comma y2 tensored over f, more y2 to y3, goes to more y1 to y3 via the map which sends a morphism f tensor to morphism g to g composed with f in the top row. And then the vertical arrows here are the same homotopy equivalences given by this theorem of Lipschitz, Oshvat, and Thurston, And the bottom row is CF hat of some manifolds that I will just tell you what they are in a second. Y12 tensor over F CF hat Y23 goes to CF hat Y13 via the map induced by this cobordism W, where here Yij is defined to be minus Yi union along the boundary with Yj. It's worth noting that this map on the bottom here is defined using, in its sort of initial formulation, the original formulation of Oshvat and Szabo, this map is defined using a particular type of Heegard triple diagram for this cobordism. So it's not at all clear a priori that, well, that these are the same thing, right? In some sense, you can think of this top row as being a computation in some sort of partially wrapped Fukaya category due to work of Denis Aru. But the bottom arrow is some computation that takes place in a completely different Fukaya category, like a Fukaya category of a compact symplectic manifold with compact Lagrangians. And it depends on several auxiliary choices. Okay, now I can actually tell you about the main construction, the sort of a general construction that I'm going to care about and then specialize to a very particular setting. If I have some collection nu of bordered three manifolds Yi phi I, where these phi I are parametrizations of the boundary of Yi all by the same surface. This is some finite collection. I goes from 1 to n. I can define an algebra using the differential modules associated to each Yi, which I call H nu. This is going to be the endomorphism algebra over A of minus z of the direct sum from I equals 1 to n of CFD hat of Yi. If you're familiar with Fukaya categories, this is fairly similar to a construction that you see in a lot of papers of Paul Seidel, where he looks at endomorphism algebras of formal direct sums of Lagrangians. So there's some sort of parallel with that story here. And again, with multiplication given by the opposite composition map, F tensor G goes to G composed with F, and the morphism space is differential as before. And sure, this algebra only depends up to quasi-isomorphism on the auxiliary choices used to define the CFD hats. So this is really something that only depends on your order 3 manifolds. And if, let's say I have some other collection, say nu prime, where, let's see, I've got yj prime, phi j prime, all parametrized, all with boundary parametrized by some other surface f of z prime, and I have a single 3-manifold, let's say, call it X, which is terrible because I usually use this for 4 manifolds, but I want to distinguish it from the Yi's and Yj's, Yj primes, with left-hand boundary of x given by f of z, and right-hand boundary of x given by f of z prime, what I'm going to do is define for you an A infinity bimodule over the algebras associated to nu and nu prime. So the way we can do this is, and as I'm just about to erase, if I have a three-manifold with two boundary components, I have some invariant called CFDA hat of whatever three-manifold I started with. I can mimic this construction, the construction of these algebras, and insert x in an appropriate place to get a bimodule, which I'll call CF nu prime of x. And this is defined to be the direct sum over all I and j of more over A of minus z from yi to x tensor yj prime, where what I really mean here is CFDA hat of x box tensor CFD hat of yj prime. But if I keep writing that again and again, my arm will fall off, so let me not do that.
So what is the meaning of that? It's like you have a cobordism between between boundaries,
Yeah.
but you don't know anything about any actual cobordism between y's and y primes.
Right.
Okay.
Yeah. Okay, so this will be an A infinity bimodule. If you want to ignore the A infinity prefix here, just think of this as a differential bimodule, but this will have some interesting structure maps, which are maps mi1j from h nu ith tensor power tensored with CF nu prime of x tensor, oh, I'm running out of room, h nu prime to the jth tensor power to CF nu prime of x. And the formal definition here is a little bit terrible, but it's mi1j of h1 through hi, comma f, h1 prime through hj prime equals, okay, something called circ sub 2 plus I minus delta of j and 0. This circ map here is a higher composition operation in the category of, well, left differential modules. I really mean left type D structures. But what goes in here will be h1 through hi, f, and some other thing that I'll call hj of h1, capital Hj of h1 prime through hj prime. And what this really boils down to, because the category in which all of these modules sit is actually very nice, owing to the fact that A of minus z is a genuine differential algebra, this actually vanishes whenever the subscript is anything other than 2 or 1.
Are the MIJs determined by MI1s or?
Sorry.
You have MIJ, yes, for
Yes.
the both morphs.
Yes.
Don't you need to specify MI1 and then?
The 1 is this f. Yeah, this thing in the middle is f. That's just there to keep track of the fact that there's something in the middle.
Oh, because this is 1. Okay.
Yeah. So f is the element of this bimodule. Now, here, hj, this map here, comes from the fact that this box tensor product operation is an A infinity functor. So this is just x box blank of identity and then J blanks. Again, if you're not comfortable with A-infinity things, just think DG functor and pretend that the extra entries aren't there. At the end of the day, what happens is that, well, circ sub 2 plus I is identically 0 if I is, well, bigger than 0. What we have is a strict left action just given by composition on the left. And then the right action here will be non-strict in general. However, it's fairly easy to understand. The two actions strictly commute, if I didn't say that before. So I'll write out a couple of these. M110 of H with F is just F composed with H. Similarly on the right, M011 of F with H prime is identity box H prime composed with F. And M012 of F with H prime 1 and H prime 2, well, this is big H2 of little h1 prime, little h2 prime, composed with F, where h2 of little h1 prime, h2 prime is a homotopy between identity box h2 prime composed with identity box h1 prime and identity box h2 prime composed with h1 prime. In general, these two maps are actually not the same, they're just homotopic.
There is a canonical homotopy, or there is a homotopy canonical up to higher homotopies?
In the category of left-type D structures, there's a very clear homotopy that's given in I think it's the bimodules in Heegard-Floer homology paper. But here, in this context, there are higher homotopies in general. Yeah. And I guess one note is we can arrange for M01J to be identically 0 if J is big enough. And this just follows from the fact that we can choose a bounded model for CFDA hat of X, if you know what that means or care. And at the end of the day, the quasi-isomorphism type of this bimodule only depends on X and the three manifolds Yi and Yj prime. Okay, this is the general setup. I'll specialize this to a particular construction in a little bit, but before I do that, I have to tell you what Chovanov's bimodules for tangles are. So there's this other half of the story, which is Chovanov homology. The punchline that I'll spoil for you now is I'm going to define some deformations of Chovanov's bimodules for tangles using this general construction. So, in a paper that dates to around 2001, 2002, depending on the version you look at, Chovanov constructed algebras. Oh no, now I have a notational conflict, don't I? Oh well, I have to go with it. I'll call them curly HN, associated to two endpoints on a line, and to any Mn tangle by which I mean a tangle diagram with 2m left endpoints and 2n right endpoints, a complex of HN bimodules, which I will denote by C sub kh of t, which have the following properties. One, the homotopy type of ckh of t is a tangle invariant, by which I mean it's an isotopy invariant of the tangle in disk cross interval represented by the diagram T. And two, it satisfies a gluing property. Namely, that if I have two tangles T1 and T2 glued together along a common boundary, and I look at the bimodule associated to this tangle diagram, this is actually isomorphic to the tensor product of the two complexes. So ckh of T1 tensored over Hn with ckh of T2, where in the middle I've got two n strands running between T1 and T2, which is fantastic. Remember this gluing property because this will tell you right away that the Hochschild homologies of these algebras with coefficients in these bimodules should be something interesting. At the very least, they should be annular link invariants, but more is true. And the critical ingredient is the 2D TQFT associated to the commutative Frobenius algebra f adjoint x mod x squared with co-multiplication delta given by 1 goes to 1 tensor x plus x tensor 1, and x goes to x tensor x. And I will tell you how in just a second. Oh, and I should tell you that this carries an internal grading. I'm going to use the old-fashioned convention where 1 sits in grading 1 and x sits in grading minus 1. The more modern convention is actually to think of this as the cohomology of CP1 shifted down in degree by 1, where x sits in degree 1. But such is life. This convention is slightly more convenient for what I'm doing. Oh, and one last remark about this side of the board. These bimodules are what are called sweet. So they're both left projective and right projective, but not necessarily biprojective. And the biprojective bimodules are characterized as those for which the tangle can be, the tangle diagram can be changed by some sequence of Reidemeister moves so that it has through degree 0. So there's some place where you can cut the tangle in half without slicing through any of the strands. Okay, so how do we define curly HN? What I'm going to do is I'm going to let Cn be the set of crossingless matchings on 2 endpoints. In other words, these should be diagrams consisting of 2 endpoints in a vertical line and half-circular arcs pairing them up. So, e.g., if, say, n is 3, the following are some examples of crossingless matchings. And the way we get this algebra is by defining it to be q to the minus n of the direct sum of all a and b in Cn of ckh of what I call A shriek B, where ckh of A shriek B is just the result of applying this 2D TQFT to the planar unlinked diagram A shriek B, which is just defined by turning A backwards and gluing it to B along their common boundary. And the multiplication operation is given by maps induced by minimal saddle cobordisms. So what are these? So M from Hn tensor Hn to N given, q to the minus n here is a grading shift downward by minus n so that the identity sits in gradient 0. This is given on some n's of the form ckh A shriek B tensor ckh of B shriek C going to ckh of A shriek C by the map induced by extending the saddle cobordism, which I'll call sigma sub B, which goes from B disjoint union B shriek to the identity braid, which, like I said, it's this minimal saddle cobordism. What you do, more or less, is you attach one handles along each component of B and the corresponding component of B shriek in such a way that you go from outside inward. So, e.g., if B is this crossingless matching, sigma sub B is going to look something like the following. I'm going to put the identity braid on the top, and I'll extend downward here like this. Something like that. Looks like a collection of saddles stacked on top of each other. And you just extend this by the identity on A and the identity on A shriek and the identity cobordism on C. And this gives you some cobordism of planar unlinked diagrams, and because we've applied a 2D TQFT, this gives us some linear maps. So, for example, if I multiply this bean shape labeled by 1 with the other bean shape labeled by 1, the first thing that's going to happen is I'm going to merge these two circles together here. That's going to be a multiplication, so I'm going to end up with this funny circle labeled by 1 again, but then I have to merge along here, and this is going to split this into two components, so I get the co-multiplication map, which was given by 1 goes to 1 tensor x plus x tensor 1. So I get a circle labeled by 1 next to a circle labeled by x, plus the circle labeled by x next to the circle labeled by 1 in the other order. So, huzzah. Okay, great. And then to define these bimodules, well, you do almost exactly the same thing for planar tangles. We'll define ckh up to an overall bigrading shift by, now if t has 2m left endpoints and 2n right endpoints, I take A to be in Cm, B will be in Cn, and I'll apply ckh of A shriek Tb. And what I do with the crossing is, well, I'll replace a crossing of this type with the formal cone, which goes from the vertical resolution to the horizontal resolution shifted in quantum grading by 1. And then there's some global bigrading shift out front here, which I'm going to ignore. Okay, great. A theorem due to Rosensky. Remember I said that the Hochschild homologies of these bimodules are sort of interesting. Well, Rosensky actually tells us that the Hochschild homology of, let's see, Hochschild homology of CKH of T, chalk is dying. Is that green visible to everyone on the board? Okay, great. This is an invariant of the closure of T in S1 cross S2. So a priori you would expect that you would get an invariant of links in S1 cross D2 just by gluing up this cylinder to itself, just by the trace property of Hochschild homology in this gluing theorem. But actually you get a little more freedom in how you move your tangle around, and you can actually sweep it around the southern hemisphere of S2. And this categorifies the stable SU2 Witten-Reshetik-Turayev invariance. Okay. Just as a quick example for a computation that's not too hard to do, at least if you work over F2, the Hochschild homology of CKH of the two-stranded identity braid, just as a vector space, or a graded vector space, is isomorphic to Q inverse F adjoin X mod X squared tensored with F adjoin H, where H is a bigraded variable of degree -1, -2, where this first grading is the homological grading, and -2 is the quantum grading, the internal grading, coming from the TQFT. Okay, so what's the observation here? Well, I told you that Chobanov homology and Heegard-Floer homology are related by a spectral sequence, and you might hope, as I will in fact show you, that there should be a similar relationship between the Hochschild homology of these bimodules and some kind of Hochschild homology of some bimodule defined using Floer theory. And that's what I'm going to sketch for you in this last part of the talk. And before I do that, I'm actually going to tell you what Hochschild homology for A-infinity bimodules is. So if M is an A-infinity bimodule over an A-infinity algebra A, the A-infinity Hochschild complex of M, I really should say of A with coefficients in M, but I'm just going to abbreviate this as M, is the quotient vector space CH of M given by M tensored over K, everything here is over K, with the tensor algebra of A, possibly with some grading shift. Typically there's a grading shift of 1 here. modulo some relation. This relation is the linear relation generated by setting E dot x tensor A1 through AK to be equivalent to x tensor A1 through AK dot E, where x is in M, the AI are in A, and E is an element of K. So remember, K is some ring spanned by some idempotents. So this in general is going to be a non-trivial quotient because, well, if you have some idempotent that acts non-trivially on the right on AK, but it kills X on the left, then you get something 0 in the quotient. And, okay, we're going to set X bar A1 dot 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 through AK to be the equivalence class of X tensor A1 through AK. And the differential of X bar A1 through AK is defined by a very big sum. You sum over all I plus j less than or equal to k, mi1j of ak minus I plus 1 through, oh, here I'm running out of space. K, x, a1 through aj, bar aj plus 1 through ak minus I, and then you add to this another sum, this time summing over all pairs I and j, where I is less than j, between 1 and k. X bar a1 bar mu j minus I, ai through aj minus 1, up to ak. So here the mi1j's are the structure maps of M, and the mu's, the mu i's are the structure maps of A. And there are some special cases when mi1j is 0 for any I and j not equal to 1, 0 or 0, 1, and the mu i's all vanish except for mu2. That's just the ordinary Hochschild complex of an associative algebra with coefficients in a bimodule. And if you allow sort of m0, 1, 0 and mu1 to be non-zero, that's the Hochschild complex of a differential algebra with coefficients in a differential bimodule.
So the obvious mixed terms can be shown not to contribute, yes? Because you could have terms with m and mu, but they you will not.
That's right, yeah. Okay. And an observation is that this complex is filtered by word length, by which I mean the length of the tensor in a homogeneous summand. In the ordinary in the ordinary setting of Hochschild homology, without all this A infinity nonsense, this actually gives you a genuine grading, but because you can collapse down some very long terms using these structure maps in the A infinity Hochschild complex, in general this is only a filtration. And a lemma of Mesher from 2016 tells us that the length filtration is weakly convergent. This is a technical detail that I'll need. And a corollary of this, very quick corollary of this, is that if M has a finite filtration, then so is the total filtration will also be weakly convergent. Okay, and as a consequence, call this a theorem, it's really more of a lemma. There is a, or I should say, the spectral sequence associated to the total filtration converges to the Hochschild homology of M, which is to say the homology of the Hochschild complex of M. And moreover, this has E2 page given by the ordinary Hochschild homology of the homology of the associated graded object of M. Okay, I need to actually tell you, say one more word about this. This E2 page, in this E2 page, we actually regard the algebra that shows up here is the homology algebra of A regarded only as an associative algebra. So the higher product operations actually don't contribute here, and we regard the homology of the associated graded object as an ordinary bimodule, or ordinary differential bimodule. The combinatorics just work out very nicely here. Okay.
So M is filtered, yes, okay.
Yes, M is a filtered A infinity bimodule over A. Okay, so there's a lot of heavy algebra that goes into this, but finally I can actually tell you about the thing that this talk is really about, which is my favorite special case. I'm going to let Bn be the set of crossingless matchings on 2n plus 2 points given by taking a crossingless matching on 2n points and putting a little arc beneath it, in which case I can look at what I call sigma of A. This is the branched double cover of A in the 3-ball, and here I regard A as having its endpoints on the equator. I think of A as living in a disk with bound to the equator of V3, and I'm going to let mu n be the collection of all of these sigma A's, where A is in Bn. That's right. I meant to call this smaller crossingless matching C. A is supposed to live in Bn, C lives in C. Okay, it turns out that all of these branch double covers have a common boundary parameterization by the so-called genus N linear pointed matched circle. So I can then go ahead and define fractor Hn to be, well, fractor nu n. So this is, again, the endomorphism algebra over minus what I call Zn of the direct sum over all A and B n of CFD hat of the branch double cover of A. I've run out of space. So theorem, the thing that sort of makes this whole story go, is that this algebra turns out to be a deformation of Chovanov's arc algebras. And it turns out to be a very highly non-trivial deformation. I'll explain in a second. But the first theorem about this thing says that as associative algebras that is to say, forgetting any possible higher operations, that arise from the homological perturbation lemma, the homology of Hn, Fraktur Hn, with the multiplication induced by the opposite composition map is actually isomorphic to curly Hn. Okay. This is very nice. So the question that you ask yourself is, well, is this actually true as A-infinity algebras? And the answer is no. Very much no. So the follow-up to this is not true as A-infinity algebras. This actually made my life very difficult for a while. And here's the one proof sketch I will give you. One can show that for all n, there exists a homologically injective embedding from Hn into Hn plus 1, and a painful computation shows that one can find a sequence of elements of the homology algebra of H2 such that, one, the induced M3 of these three things is non-zero, and that this is in fact independent of the choice of retract in defining the higher A-infinity operation. So there's no way to get rid of the higher homotopical data of H2, and since H2 is going to include into all higher HNs homologically injectively, this will also tell us that M3 is going to be non-vanishing. In fact, this situation is even worse. All of the MNs are non-vanishing for n greater than 2 on the homology of H2. A conjecture which I won't write on the board is that this has something to do with an A-infinity module structure over F adjoin x mod x squared that shows up in a paper of Lipschitz and Sharkar. But I haven't proven this yet, but I expect to reasonably soon. Okay. And just as, to give an example, or to actually sort of make this a little bit more visual and show you what this looks like at the level of Chovanov's arc algebras, the sort of first example that I found of a non-vanishing M3 in that context looks like M3 of this little bean labeled by 1, this element, a linear combination of two circles, and then the other bean labeled by 1. This ends up giving us two nested circles, one labeled 1, one labeled by x, and another one where 1 and x are reversed. Great. There it is. How am I on time? I have just enough time. Great. Okay. So lastly, given an NN tangle T, so again, this has 2n left endpoints and 2n right endpoints, I'm going to define a new tangle diagram T plus by just taking T and inserting two strands beneath it. And I'm going to let sigma of T plus be the branch double cover of T plus, regarded as a tangle in 0, 1 cross S2. Again, the endpoints will live on the equator of the respective boundary components. And a theorem of Lipschitz, Schwarz, and Thurston tells us that this CFDA hat of sigma of T plus, not stated quite in this way, but this is a consequence of it, this admits a filtration with the property that if I have any two crossingless matchings A and B in Cn plus 1, I'm going to state it this way. The homology of the associated graded of the morphism complex from, I'm going to abuse notation terribly right now, from A to T plus box B. So here I mean, take branch double covers of every tangle diagram in sight, and then take either CFD hat or CFDA hat. Homology of the associated graded. Apologies. It is isomorphic to CKH of A shriek T plus B. And as a consequence, if I define, if I define the branched Floer complex CF beta of T to be this CF nu n of the branch double cover of T plus, then it turns out that the homology of the associated graded object of CF beta of T is, well, the same thing as CKH of T, turns out. And finally, as a consequence of all of the general algebraic stuff that I set up before, there is a spectral sequence from the Hochschild homology of CKH of T converging to the A infinity Hochschild homology of CF beta of T. And very nearly out of time, so I will say one more thing. Another theorem. What may be of independent interest is that these A infinity bimodules also satisfy a gluing property. So CF beta of T1, T2 is homotopy equivalent to CF beta, or let's say quasi-isomorphic to CF beta of T1, derived tensor product, CF beta of T2. And the proof of this theorem goes through the existence of the Schwarz-Sabo spectral sequence. It is, I don't currently know under which general properties of the collection of order 3 manifolds I used to define my algebra, a similar gluing theorem would hold more generally. So I'm currently thinking about that a bit. And another interesting question is, one could ask potentially how this A infinity Hochschild homology is related to not Floer homology. This is very, very similar in flavor to the A infinity Hochschild homology of just CFDA hat of the branch double cover of T plus, which one can realize is not Floer homology via a paper of Lipschitz and Sherman. Okay, that's all I had to say today.
Any questions?
Just a very naive question.
Sure.
Okay. In BN, you added this extra strand.
Yes.
And also in T plus, you added these extra strands. Like, what are the holes?
So yes, this is a great point. So in the original Oshot and Szabo paper, what's proven is that there's a spectral sequence from the reduced Chavanov homology of the mirror of a link. Oh, I should put a mirror here. Apologies. From the reduced Chavanov homology of the mirror of a link to HF hat of the branch double cover of L. And there's a bit of a mismatch here because, what should I say? Sorry, that should be an arrow. In order to get ordinary Chavanov homology here, you can add an unknot far away from L. Because this turns out to just be, the ordinary Chavanov homology in characteristic 2 is just isomorphic to the reduced Chavanov homology tensored with f adjoint x mod x squared. And this depends on some choice of base point, but in characteristic 2 that doesn't matter. And in some sense, so what happened here, and this threw me for a very long time when I was working on this, is that if you don't work in the unreduced setting, and you try to define your algebras and your bimodules by way of analogy with Chavanov's bimodules and algebras, you're doubly reducing everything. So, for example, what happens if you look at sort of the simplest case, you would end up with the reduced Chavanov-Arc algebra on 2 points, and just a very, very simple, you'd also end up with the reduced Chavanov bimodule of the two-stranded identity braid. And those are both F. So you end up taking Hochschild homology of F with coefficients in F, which is just F. But, well, the sort of Hochschild homology of the closure of the two-stranded identity braid in S1 cross S2 is infinite dimensional. So one option is to try to singly reduce everything, but then on the Heegard-Floer side, it's not clear what you should be taking the branch double cover of. So my solution was, well, let's just unreduce everything by adding in these extra arcs and these extra strands.
Do you have anything like Chavanov-Floer theories for your framework? Can you put it in the context of like general Chavanov-Floer theories?
That's a great question. Let's maybe talk a little bit more about that later, but partially work in progress with someone else. Yeah.
Okay, any other questions? Okay, so if not, let's thank Jesse again. Okay, so for today, it was the last lecture. See you all tomorrow.
Sorry for interrupting. I really wanted to get at least some understanding. So if you say that it's associative algebra, don't you imply that